Hello and welcome to another exciting math video. This video is going to cover 3-6 in the calculus book, optimization problems. And we'll see that here in a minute, but here's the assignment for this section, page 262 in the text. These three are smaller ones, simpler ones that are available on WebAssign. And then here are 5 problems, actually 6. 34 is optional, but these are out of the textbook. Okay. So this is 3-6 optimization. It seems simple enough. There's only one bullet point. Solve applied min and max problems. So all that stuff we did with finding mins and maxes, now this is just a like a real world application section of those types of problems. And then the book goes on to say one of the most common applications of calculus involves the determination of minimum and maximum values. Consider how frequently you hear or read terms such as greatest profit, least cost, least time, greatest voltage, optimum size, least size, greatest strength, or greatest distance. And then it says, before outlining a general problem-solving strategies, let's consider the next example. Actually, I moved that slide up. This is in your notes, but it's after example 1. And I figure if there's a guideline for it, why not introduce it right away, even before we do example 1. So let me get my highlighter ready. Identify all the given quantities and quantities to be determined. If possible, make a sketch. That's very helpful. Number 2, write the primary equation for the quantity. This is what we are going to maximize or minimize. The equation we want to min or max is our primary. At some point, we will have to derive it. Number 3, reduce that primary equation to 1 having a single independent variable. One independent variable. This may involve the use of a secondary equation that has the same independent variables as the primary. We might even need more than one secondary equation. Number 4 is not super critical for most problems. If you forget this part, it usually won't hurt you, but sometimes it does if our min or max occurs at an endpoint. It says here, determine the feasible domain of that primary equation, or what values, usually of x, does the stated problem make sense. Again, most of the time it's not going to be critical to finding the correct answer, but it does pop up. Number 5, we actually do some calc. Determine the desired min or max by the calc techniques we saw in the last few sections. Okay, so let's dive right in here with example 1. This is a very staple box problem. You see them in most every calc book. So we have a manufacturer. They want to design an open box, so there's no lid on it, that has a square base. Let me highlight that. That's pretty important. The surface area is limited to 108 square inches. What dimensions will produce a box with maximum volume? Okay, so here's our picture. The base of the box is a square. So they just use variable x. X times x is the base. And then the height of the box is represented by the variable h. So from those guidelines, we do want to find a primary equation. And remember, that is what we want to minimize or maximize. And here it says maximize volume. So volume equals the volume of this box is going to be length times width times height, or x times x, which is x squared. There's our base, and we're going to multiply that by the height of the box. So there is our volume, our primary equation. Now the secondary equation is going to involve the same variables, and this will usually have the constraint of the problem if there is one. It says here our surface area is limited to 108 square inches. So what is the surface area of our box? Okay, the surface area of just the base of it is going to be x times x, that's x squared, plus the box has 4 sides, 1, 2, 3, 4. So we have 4 equal sides, and each side has the area of base x times height h. So here are the 5 pieces to our box, the surface area, and that is limited to 108 square inches. Okay, so we've got our primary and our secondary. The usual steps now are to solve the secondary to get it down to one variable. So like in this case, we're going to get h by itself, and then we're going to take that h and plug it in for this h in our primary equation. Okay, so let's solve this for h. So we've got 4xh. We're going to have our 108 over on the other side and subtract the x squared. Now to get h alone, we're going to divide everything by 4x. So I'm going to just put a big division line here and divide all of that by 4x. So that is our h. H equals. So I'm going to start a new slide here. I don't want to erase anything. And I'm going to rewrite this equation. Volume equals x squared h. Volume equals x squared. But now instead of that h, I'm going to multiply by this. 108 minus x squared over 4x. 108 minus x squared over 4x. Okay, so let's see here, a little algebra to clean this up. The first thing on the diagonal, we can cancel this x with one of these, so those are gone. And if we distribute the x, this will be 108x over 4, and 108 divided by 4 is 27. So that becomes a 27x. And we distribute the x to the minus x squared, so that is a minus x cubed. But remember, we divided the 108 by the 4 to get 27, so this is a 1/4 x cubed. So there's our primary equation in one variable. Primary in one variable. So that'll make this very easy to derive and find the min or the max. Okay, I almost forgot myself. Remember I said it's not that critical sometimes to determine the feasible domain. Well, let's look at it here. So what is the domain of x? How small or how big can we make x? I always like to go back to my picture. So look here. X is the side of one of these pieces of our square base. So how small could we make x? Well, we could make x very, very tiny. Use very little cardboard on the base, and we'd use all the remaining cardboard to build the sides of our box. So theoretically, we could make x almost as small as 0. Again, that would be having no base and using all the cardboard on the walls of the box. And then theoretically, how big could we make x? Again, think about the base. This is x times x. So the area of the base is x squared. And if we used every square inch of cardboard just on the base, we would set x squared equal to 108, or x would equal the root of 108. So here is our feasible domain. X has to be a number between 0 and a little bit more than 10. Our final answer should be in there, or we know something went wrong. Again, if we had skipped this step, we could still get to the right answer. Okay, here we are. Let's derive with respect to x. dv dx equals derivative of 27x is 27. Derivative of 1/4 x cubed is 3/4 x squared. So we've got our derivative. And how do we find mins and maxes? Well, we set that derivative equal to 0 to find our critical numbers. So if we set this equal to 0, I'm going to add the negative 3/4 x squared, but I'm going to move it to the other side, and then that's going to equal 27. So again, if this jumped over, it would be positive, and now it's these two are positive equal to each other. And then let's see here. If we multiply by the reciprocal, 4/3, 27 times 4/3 is equal to 36. X squared equals 36. And obviously take the square root. If we root both sides, we get plus and minus 6. But remember, this is an applied problem, and x is the length of this side of the box. Can you grab a ruler and measure something as having a negative length? No. So the negative is nonsensical. I can throw the negative in the garbage. And now we've got x equals 6. Now it's a good answer, but remember they asked us for what were the dimensions of the box. This is only one of the dimensions. So our box's base is going to be 6 by 6, but how much cardboard does that leave to build the walls of our box? So we've got x. How do we solve for h? Well, let's back up and look at that secondary equation. Let me get rid of this. Our secondary has x's and h's, and it's equal to 108. So let's plug in x is 6, so that's going to be a 6 squared, plus 4 times 6 times h equals 108. So that's 36 plus 24h equals 108. And if we subtract 36, 24h equals 72. Divide both sides by 24. H is 3. So our base is 6 by 6. The height of our box is 3. And then we could find the volume. If we multiply the base and length times width times height, we get the maxed volume of the box. And I think that's it for that one. And let's check this out. Here you could solve this without calculus, just with some trial and error. Remember, we're limited to 108 square inches of cardboard. So here we might try making our base 3 by 3. If we use our bases 3 by 3, that leaves 8 1/4 to make the height of the walls. We have enough cardboard to make very tall walls. If we find the volume, it's a little more than 74 cubic inches. So if a 3 by 3 base gave us that volume, what about a 4 by 4? We have a bigger base, so that means less cardboard for the height, so this box won't be as tall, but the volume has increased up to 92. So 4 by 4 worked. Let's jump it up to 5 by 5. If we do that, we have less cardboard for the height of the walls. Now our walls are just a little more than 4 inches, but our volume has increased again. Now we're up to over 104 cubic inches. So here's our box. We went 5, 5. Here's our box, 6 by 6 by 3. If we find the volume of that, it's 108 cubic inches. So we keep making our base sides bigger and bigger, and our volume kept increasing. But now if we increase it more, if we go up to an 8 by 8 base, our walls are not nearly as tall, and this affects our volume. Now it is decreasing. We went from 108 down to 88. So we found our sweet spot, the one measurement for x that's going to maximize the volume of that box. What's next? Example 2. Which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? So here is our equation, 4 minus x squared, downward opening parabola, y-intercept of 4. It will cross the x-axis at plus and minus 2. On the y-axis, I'll hit it in blue as this point 0, 2. If we're up here, we are 2 units away from that point. But as we start working our way down, we get closer and closer and closer to this point 0, 2. But then after that, we start to increase our distance away from that fixed point again. So somewhere on this parabola, and I'll just highlight them here in red, this point is as close as you can get to the point 0, 2. And because of the symmetry, there's another point over here that is also that distance away from the set point 0, 2. Okay. So our primary, what are we trying to minimize or maximize? If I bring this back down, it says finding minimum distance. We want to minimize the distance between our parabola and that fixed point. Do we have an equation for distance? You betcha. Distance equals big old square root x minus h quantity squared plus y minus k quantity squared, the good old distance formula. Now to get rid of some of those variables, this point 0, 2, our fixed point, is the h and the k. H is 0, k is 2. So let's plug those in. So this h is going to turn into a 0, so that's going to be x minus 0 quantity squared, which is just x squared. And then our k value is 2. So that becomes y minus 2 quantity squared. There is our primary equation. We do want to minimize this, so it is going to need derived at some point, but not right yet. What is our secondary equation? Now, if you reread the problem, there's not much to work with. The only thing left is y equals 4 minus x squared. Y equals 4 minus x squared. We got a primary, we have a secondary. We're going to put the secondary into the primary to get it down to one variable. Right now, I'll underline in green, we've got x's and y's. I like to get it to be all just x's. So this, we don't even have to manipulate our secondary. Here is y equals this stuff. I'll put it in green parenthesis. That stuff in the parenthesis is going to go in for that variable y. So I'm going to write it down here. We've got x squared plus parenthesis. This y is gone. Y is replaced with 4 minus x squared. But don't forget, we still have this minus 2. And then that quantity is squared. Oops. So here is my primary equation in one variable. Now I should be able to copy this onto a new slide. Copy. Paste. And there we go. Okay, let's do a little algebra to clean this up before we have to derive it. Okay, so we've got a big old radical. First we have an x squared, that's not going to change. But in the parenthesis, the 4 and the minus 2 is going to become a 2. And then we have minus x squared, and that quantity is squared. Ooh, this looks like it's going to be fun to derive. But let's do a little foiling and combining like terms. So we've got our x squared plus. If we FOIL this out, first times first is 4. And then we're going to have this times 2. So that's a 2x squared, and we're going to double that to a 4x squared. Oop, and that should be a minus in between them. Minus 4x squared. And then negative x squared times negative x squared is positive x to the 4th. Here is our primary equation in one variable. Now, and let's back up. Let's talk feasible domain. So we're talking, we're putting in x's. How small and how big of x's can we put in? Remember, this is just a polynomial equation. I could put in x as negative 1,000,000. I could put in positive 1,000,000,000. For here, our domain is going to be all real numbers. We can put in any number we want. Of course, some of them are going to give us our sweet spot very close to that fixed points. Other ones are going to be very far away. But in this case, our feasible domain is all real numbers. Ooh, and I guess I forgot we can combine these x squareds. We got an x squared and a minus 4x squared. And let's put this in descending order. X to the 4th minus 3x squared plus 4, all under a radical. Now, we do have to derive this, but let's make our lives easy and put our thinking caps on. We have this big old radical over the whole problem. Does square rooting something make it grow or shrink? It always makes it shrink. The square root of 16 is 4. It shrinks. The square root of 100 is 10. So when you square root 100, it shrinks. No matter what, when you square root something, it's going to become smaller. And then, so we can get away with this. Let me write it out. To minimize a radical, minimize what is under the radical. Minimize what is under the radical. Because, if we minimize this stuff that's under the radical and get it as small as possible, when we square root that, it's going to get even smaller. So to make life easy, we can ignore the radical at this point in this specific problem. So we're just going to get rid of the radical. We've got x to the 4th minus 3x squared plus 4. We'll just call that f of x, because now we're going to derive it, f prime, and that is 4x cubed minus 6x. The 4 derives away. As usual, we set our derivative equal to 0. And I'm going to factor out a 2x, leaving 2x squared minus 3 in the parenthesis, and that's equal to 0. Now, if we set the first component, 2x, there we go. If we set 2x equal to 0, we get x equals 0. And what about here? Well, let's see. X equals. The first thing we're going to do is add 3 to both sides, so now it's a positive 3 on the other side. We're going to divide by 2 to get the x squared alone, and then to get x squared down to x, we're going to take the square root. Don't forget the plus and minus. So here are the critical numbers. If we look at this, x is 0. Get back there. Here's x is 0. On our picture, that is this. And you might think, oh, that's a max. It's the top of a hill. But remember, what we're doing here is maximizing our distance away from our fixed point. So if we analyze this, here we're as close as we are to our fixed point right now. We're getting farther away, farther away, farther away, farther away, until we get over here. Now we're getting closer again. So it is a local max for the distance away from the point. But we were trying to minimize. And if we do the first derivative test on the plus or minus root of 1.5, we'll find that that is a minimum distance. And if we go back to the picture, let me get rid of this. So this point over here is our positive root of 3/2 comma something. And on the other side, this would be our negative root of 3/2 comma something else. Let's find the y values. Our equation was y equals 4 minus x squared. Y equals 4 minus, and here is our x. We're going to put something in there and square it. And what we're squaring is our radical, 3 over 2. And this y value will be the same for both because we would just square this negative away. So if we square that, we're going to get 4 minus 3 over 2 square rooted. If you square it, it's just going to become 3 over 2 or 1.5. And 4 minus 1.5 is 2.5, so we could put 2.5 in there. I prefer fractions, so I'm going to write it as 5/2. So our root of 3/2 comma 5/2 is the minimized distance away from that fixed point, as is its reflected twin at negative root of 3/2 comma 5/2. Okay, and I think that's all they're asking for in that problem. Yeah, so there's example 2. Example 3 is about a print on a page. This one's pretty interesting. Let's construct our picture from scratch here. So we want a rectangular page. Ooh, I might be able to do this. So we've got a rectangular page of paper. It's to contain 24 square inches of print. So we're going to have a rectangle in our rectangle. And we want this rectangle to be the printed area, and that's going to be 24 square inches. Margins in the top and the bottom are 1.5. Margins left and right are 1. So let me put that in there. And I am going to call in here, this blue side is x, this blue side is y. And then we've got our margins, 1.5 at the top and the bottom. And then left to right is 1 inch. 1 inch. What dimensions of the page should be so that the least amount of paper is used? Okay, so what we want to do is minimize this area. We want to minimize the entire sheet of paper, make it as small as possible to save on our printing costs. So what is the area of that paper? Well, it's not x times y. That's the blue area in the printed part here. So let's see. This side is x, and we've got 1.5 inches up here and 1.5 inches down here. So that side is going to be x plus 3. 1.5 inches and another 1.5 inches is 3. So that is this side of the paper. And if we want to find the area, we got to multiply it by this side. Well, that side is y plus the margins. So we've got y plus inch on the left, inch on the right. Adds up to 2 inches. So here is our area equation. The area of the entire page is x minus 3 times y plus 2 as a quantity. When I should write that as our primary. Primary there. The secondary. We need to use the same variables, and like I said, this usually involves the constraint. Now it says here, rectangular pages do contain 24 inches of print, and that's this blue box in here. This should be 24 square inches. How do we find that area? Well, it's x times y. X times y equals 24. So we've got a primary, we've got a secondary. We're going to solve the secondary for one variable and plug it into that primary. I'm partial to leaving x's in my equations, so let's solve this for y. Y equals 24 over x. So I'm going to start a new slide here. The first thing is I'm going to bring over this term. X minus 3 is a quantity. Area equals x minus 3. And we're going to multiply that by this, y plus 2, but that y is out. It's going to be 24 over x plus 2. 24, that's a terrible looking 4. 24 over x plus 2. So there's our primary equation in one variable. Now we could derive it in this form using the product rule, but it might be easier to FOIL stuff out and just use power rule. And I almost forgot again. Let's go back, think feasible domain. The feasible domain. Again, how small or how big can we theoretically make x? So this side is x. We could make x very, very small. Remember, that's the printed area. What if we go 1/10 of an inch tall and it would have to go out many, many inches? It would be a huge, very wide, very slim printed area. But we could do it. We could actually make x almost down to 0. So that would be, we would have no height. Our printed area would be all width. On the other hand, we could go in the other direction and make x infinitely tall almost, and we'd have very little left over for the width of y. So we could say theoretically this could almost go to infinity. So here x just has to be a positive number. Remember, because that is a side length of our printed area, x must be positive. Okay, back to here. Let's FOIL. First term times first term, 24x over x. That's going to divide out to a 24. First times, or our outers is 2 times x. Minus our inners, negative 3 times 24. Well, that's going to be a 72 over x. And then last times last is negative 6. And let's write this in the proper order. I'm going to put the... Let's see, the 2x goes first, and then we're going to have minus 72x to the negative 1, and then we've got 24 minus 6, no, hold on here. Why is that x minus 3? That should be x plus 3. What the heck am I doing? So these are all pluses. My bad. That's not going to hurt too much in your note taking, I think. Okay, so this is a plus. Yeah, and then the 24 and the 6, that's going to add up to 30. There we go. So here is our primary equation in one variable, ready to derive. Let's go. Derivative of area with respect to the x variable is derivative of 2x is 2. And then this will become minus 72x to the negative 2. So that'll become over x squared, and the 30 derives away. So there is our derivative. Let's set it equal to 0. And we'll add the 72 over x squared to each side. So now that's over here and it's positive. Let's multiply both sides by x squared. So now 2x squared is equal to 72. divide by 2, x squared equals 36. And if we take the derivative of that, we get plus or minus 6. But again, the negative 6 will make no sense in the context of this applied problem. So we just found x is equal to 6. Okay, so let me go back to the picture. This x here, this side is 6. So what should y be? How are we going to find y? Well, we go back to our secondary equation. Let me erase this stuff down here. There's our secondary in blue. We found out that x is equal to 6, so that's 6y equals 24. Divide by 6, y is 4. So the printed part of our page is 4 by 6. Now, if this was multiple choice on the AP, that would be the first decoy answer, because you'd think you'd got it and you'd jump on there and mark it and get it wrong. Remember, we're trying to minimize the dimensions of the whole page. So we need to take that 6 and 4, that is our printed area. We need to add in the margins. Remember, the margins at the top and the bottom were 1.5 each, 1.5, 1.5. So this 6 gets 3 added to it. So this side of the paper is 9 inches. And then this 4 gets a 1-inch margin on the left and 1 inch on the right. 4 plus those margins is 6. So the paper should be 6 by 9. A 6 by 9 page with a 4 by 6 area printed on it has the margins, and that will minimize the cost of the paper. All right. What's next? I think they're going to get a little trickier. Ooh, here we go. The wire problem. And I guess I'll leave the picture here instead of on a new slide. And shoot, I should have whited that out. So don't give it away. Ooh, and actually, let's do this. 2 posts. Well, yeah, let's stick with the picture. 2 posts. One's 12 foot, the other's 28. So here's the short one on the left, 12. Higher one on the right is 28. They are 30 feet apart. So this entire distance is 30 feet. They're to be stayed by 2 wires attached to a single stake running from the ground level to the top of each post. Where should we put the stake to use the least amount of wire? And actually, I am going to sort of draw this myself. So here we go. And I'll use red, so we're going to put a spike somewhere in between these posts and attach a wire from the top of each to the spike. And we're going to just call this distance here from the short pole to the spike, let's call that x. And then, of course, this entire distance from pole to pole is 30. So that makes this distance 30 minus x. Okay, this is 12, this is 28. And then I'm going to use green ink on the wire. So this that I'm highlighting in green is the guy wire, and we want to minimize that length. We want to make that as small as possible. Well, just for variable's sake, let's call this length y. And then this longer one over here is z. Okay, I think we have enough. Let's come up with our primary equation. Remember, the primary is what we want to minimize and maximize, and that is the highlighted green wire. So we want to we'll just call that capital W. W is equal to y plus z. Y plus z. So there's our primary equation. The wire, W, is equal to the y length plus the z length. This is our primary. This is what we are going to minimize or maximize at some point. Now, the secondary equation, or equations. We're going to need more than one. So the secondaries. Remember, we need the same variables that are going to relate it all together. So this length here, y, on the small triangle, and we have this side, which we have defined as x. This side, 12, is not going to change. So we could do Pythagorean Theorem. X squared plus 12 squared equals y squared. X squared plus 12 squared, I'm just going to write that as 144, is equal to y squared And if we square root both sides, we're going to get y equals radical x squared plus 144. There we go. And let me get this out of the way so I can do this. There we go. So there's our first secondary equation. Y is equal to that radical. And of course, this y is going to be replaced with that radical at some point. But we got to do something similar for the z variable. Here's z, and it's going to be a Pythagorean triangle again. So on this one, we have the base is 30 minus x, that leg squared, plus 28 squared is equal to z squared. Z squared. Okay, and let's see, to save a little time in the video, if we FOIL this out and we square the 28 and we combine the like terms and then we take the square root to get z by itself, no longer z squared, this is what we're going to come up with. Z equals big old square root x squared minus 60x plus 1,684. Okay, so we've got our primary in blue, we've got our secondaries in red and black ink, and now I'm just going to take this y out, replace it with the red radical. I'm going to take this z out and replace it with the black radical. And let me go to here. So w equals square root x squared plus 144 under the radical plus square root x squared minus 60x plus 1,684. Now we're getting to the point, really soon we're going to have to derive here. And you see the radicals. Now don't think because we're going to minimize this, we just minimize what's under the radicals. In this case, remember this x is not the length of the wire. X is this distance here. How far away from the left pole are we going to plant that spike? So that's not what we're trying to minimize. So we're not just going to ignore the radicals in this case. So this is going to be a little bit trickier of a derivative. And let me do this. Remember, a radical, this is just to the half power. So dw dx, when we derive with respect to x, we're going to bring the half down front. And then we're going to have the exact same quantity, but now to the negative a half power. And don't forget the good old chain rule. So we need to derive the inner function, and we're going to get a 2x. And let me just clean this up right here. So let's see, we can do the 1/2 times the 2x, so that leaves an x in the numerator. And then the negative exponent is going to take that downstairs, and I'm going to put it back under a radical. X over the root of x squared plus 144. So that's our first term. And now I'm going to do a little, get this over here. There we go. And I'll switch to blue ink for the second term plus, because we're going to have to do the same thing here to this one that I wrote in black ink. Let me get rid of some of this so I have a little more room. It's going to be very similar. It's a half power with the radical, so the half comes down front. We will have the same quantity inside, but now it's to the negative a half, and we need to multiply by the chain rule. That's going to be a 2x minus 60. Minus 60. Okay, so we've got the 1/2 times 2x minus 60. So that's going to be x minus 30 when we cut those in half. And then the negative radical goes down to the denominator. Plus 1684. There's our derivative. What the heck do we do with it? We set it equal to 0 and solve. Equal to 0. Okay. Oops, there we are. Okay, so here, I'm going to move the one in blue over to the other side. So I'm going to keep this one over here in red. X over radical, x squared plus 144. Now, when we move that, I'm going to put a set of parentheses around the numerator. When we move that over to the other side of equals, we could just put a negative outside, or let's distribute. So that's going to be a negative x plus 30, or I'm going to write it as 30 minus x. Same song and dance. And that is equal to this radical, or has this radical on. Oops, it's supposed to be a minus. There we go. Minus 60x plus 1684. Okay, well, let's see here. I guess we could either square both sides or cross multiply. What should we do? In the past, I've cross multiplied and then squared. It might be better. I'm going to try it different this year, and let's square both sides. The left side's easy. If we square the numerator, it just becomes x squared. If we square the denominator, the radical goes away. Equals. On the other side, if we square this numerator, 30 minus x quantity squared, let's FOIL that out right now. So let's see. 30 times 30 will be 900. And then we're going to have minus 60 x's, and then plus an x squared. And then down underneath in the denominator, when we square that, the radical disappears. X squared minus 60x plus 1684. Okay, we are now radical free. And from here, we can cross multiply. So I'm going to use red ink for this one. I'm going to go this numerator times this denominator. And let's see, I might as well distribute right now to save that step. If we distribute x squared to x squared, that's x to the fourth, minus 60x to the third, plus 1,684x squared. And that is equal to the other diagonal. And let's see here, if we multiply x squared plus 144, that quantity times this trinomial, I'm just going to jump right to the answer here. Collect like terms, you're going to have x to the fourth minus 60x cubed plus 1,044x squared minus 8,640x plus 129,600. Okay, I wish I could have got those. Get back there. I didn't want to erase that red stuff. There we go. I wish I could have wrote that all on one line, because it's going to be easier to see what happens next. We are going to try to solve for x, and the beauty is the first couple terms cancel each other. If I subtract x to the fourth from the left, I subtract x to the fourth from the right, they're gone. If I add 60x cubed to the red side, I got to add 60x cubed to the blue side, so those also cancel. All right, so now it's getting down to be a little more manageable. Let's see here. If we get all our x squareds on the left, there's going to be 640 of them. And then we'll have a positive 8,640 x to the first minus 129,600. And we're going to set that equal to 0. Okay, well, let's see. We can factor out a 320. And then that'll leave a 2x squared and some other stuff. That will factor down into an x minus 9 and a 2x plus 45. All right. If we divide by 320, that's gone. If we set the first factor to 0, we get x equals positive 9. And if we set the next one equal to 0, we'll subtract 45 and divide by 2. That is a negative 22.5. And there we go. Ooh, now I almost forgot. Feasible domain. Let's back up here. Domain. Remember, this is about x. So if I blow the picture up a little bit here, remember x is this distance away from the base of the 12-foot pole. How small could we make x? Well, we could make that all the way down to 0. We could put the spike right at the base of that pole. We could run the guy wire down the pole and then up to the next pole. So that would be x is 0. And then theoretically, how big could we make x? Well, if there's 30 feet of distance between the pole, we could make x 30, and then the other little chunk would be nothing. So x must be a number between 0 and 30. And again, let me make a new slide here. This is the 12-foot pole, and over here is the 28-foot pole. X is our distance away from the base of the 12-foot pole. So our left extreme example, I could put the spike right here. We could run the line down the pole and then up to the top of the other. On the other hand, maybe we put the spike way over here and we go the wire from the top of the 12-foot pole to the spike, and then it runs straight up that one to the top of the 28-foot pole. So those are our extremes. X could be 0, X could be 30. And then the sweet spot might be somewhere in between. So we found out here, we think that x is 9 might be the sweet spot. But of course, we also want to check the endpoints. We figure out the feasible domain because the min or max might be at an endpoint. So here is our suspects. Again, we can eliminate the negative because that just doesn't make sense. And we're going to have to do our endpoints. What is W of 0? What is W of 30? And what is W of 9? The number we found that we are suspicious might be the sweet spot. So we take these back to our original equation, primary equation in one variable, and if we put a 0 in there, out pops approximately 53.04 feet. So that's how much wire it would take us to go from the top of the 12-foot pole to the base of the 12-foot pole and then right up to the top of the 28-foot pole, 53 feet of wire. If we go to the other extreme, put the pole by the base of the 28-foot pole, that is approximately 60.31 feet. So that's more wire if we do it that way. And if we plug in the 9 that we found with our calculus, out pops a nice perfect 50 feet. So we did want to check the endpoints. You might have your mins or maxes at the endpoints. This was not the case here. We found our min was at 50 feet of wire if we put the pole if we put the spike 9 foot away from the pole on the left. So let me pull out this picture one more time. If we make this distance here in blue exactly 9, that means this distance will be 21. And if we put the spike right there, we will minimize the amount of wire we need to stay the top and the bottom of that pole. All right, example 4 was a doozy. What's next? Example 5. Makes sense. Oops. There we go. Now here they spoil the surprise. It says an endpoint max. We can find our sweet spots at the endpoints. So it says here you got 4 feet of wire. You're sitting around bored and you got 4 feet of wire to play with. And you decide to form a square and then a circle from that 4 feet. You're going to use some of the wire for the square, some for the circle. How much of the wire should be used for the square and how much for the circle to enclose max total area? We want to have the most area as possible using our limited 4 feet of wire. So our primary equation is going to be about area. Area equals the total area is the area of the square plus the area of the circle. Let's go over here to our picture. What is the area of this square? Well, side is x, area is x squared. So that is the area of the circle. plus we're going to add to that the area of the circle. What is the area of a circle? Pi r squared. Okay, so that is our primary. Abbreviate PR for primary. We need a secondary. Now, where's that going to come from? Remember, we are limited to 4 feet of wire. If I were to make a square, I would lay the wire down on the table in a square shape. So what would the perimeter of that square be? Well, we got 4 sides. Each is x, so that would be 4 times x. Plus, if we were to make a wire or a circle out of the wire, we would lay the wire down in a circular shape. So the circumference of the circle would be taken up by the wire. What is the circumference of a circle? 2 pi r. Or excuse me, 2 pi r. 2 pi r. So this is the perimeter of the square, the circumference of the circle. If we add those together, we should get our limited 4 feet of wire. And that is our secondary, SEC for secondary. Okay, and we're hinging all of this on x. Ooh, and before I forget, let's do the feasible domain right now. Domain. Remember, we have 4 feet of wire. So how small could we make x? X is this side of our square. How small could we make x? Well, we could make x as small as 0. If x is 0, that means we have no square. We've used all the wire to make the circle. So this is all circle, no square. On the other hand, what if we use all of the wire on the square? Well, if we've got 4 feet of wire and each side is the same, x, get back there. X could be as high as 1. And if we did that, that would be using every bit of wire on the square. Here we do 1 foot of wire, 2 foot of wire, 3 foot of wire, 4 foot of wire. There's all our wire, and we have nothing left for the circle. So this is all square. This is all circle. What would x be for all circle or all square? There's our domain. X has to be a number between 0 and 1. Okay, let me start a new slide here. And let's get our secondary down to, our primary down to 1 variable. I'm just going to recopy the secondary here. 4x plus 2 pi r is equal to 4. Let's get r by itself. So 2 pi r stays on the left. We've got this 4, and we're going to minus the 4x. Now to get r alone, divide by 2 pi. 4 minus 4x, divide that by 2 pi. And let's see, we can divide everything by 2. R equals 2 minus 2x over pi. And I think it might be easier. Let's also factor a 2 out of that numerator. 2 times quantity 1 minus x all over pi, that's equal to r. So r equals that. So that's our secondary equation, solved for r. Remember now our primary, I'm just going to sneak up here and copy it down in red ink real quick. Our primary was x squared plus pi r squared. X squared plus pi r squared, we're going to take out that r and replace it with this quantity. So area equals x squared plus pi. In here would go the radius, and we're going to square it. But the radius is out, and we're going to replace that with 2 times quantity 1 minus x all over pi. Now, if you're thinking about canceling these, don't do it yet because we still got that squared in there. Okay, I guess it's algebra time. Let's see. This first x squared is going to stay as is. And we've got this pi out here. We're going to hold on to that for now. Now let's see, if we're squaring all the stuff in blue, don't forget we're going to square this 2 out here. 2 squared is 4. And then we're going to have 1 minus x quantity squared. I feel like foiling that out right now. 1 minus x times itself is 1 minus 2x plus x squared. Oop, that's supposed to be a squared. Don't forget to square the denominator. This pi down here also gets squared. So that becomes pi squared. Okay, we're getting somewhere. Time for more algebra. Let's keep simplifying over here. We can cancel a pi. This pi to the first is going to disappear, and this pi squared is going to get knocked down to first power. And let's see. Let's distribute the 4. So that's going to be 4 minus 8x plus 4x squared all over pi. And let's see here. We've still got this x squared out. Let's give it the common denominator. So we've got an x squared over 1. Let's make it pi x squared over pi plus. So that way we can put this all under one, or put it all over one big denominator. So, oops. See here, one big denominator. We've got common denominator pi. Upstairs, we've got a pi x squared. And I'm going to put plus 4x squared next, plus 4x squared. And then we've got a minus 8x, and a plus 4. And that's all over pi. Okay, we are going to derive this, but not just yet. Let's see here. Just a couple more things to make this a little simpler to deal with. Okay. First, I've got this denominator pi. Let's drag that out as a fraction. Pi downstairs becomes 1 over pi when we pull it out. Now, watch this. It's kind of a little weird. We've got a pi x squared and a 4x squared. So how many x squareds do we have? Well, if we just factor out the x squared, what are we left with? Pi plus 4. Pi plus 4 in parenthesis, x squared. And then we've got our minus 8x and our plus 4. All right. I think it's time to derive. Yeah, we've got our primary. It's down to one variable, just x is in there. So if we derive dA dx, 1 over pi is a constant multiple. It's going to come along for the ride. Now, this one, it looks kind of weird, but if you're deriving 3x squared, the derivative of that is 6x to the first. So this, even though we have a quantity in front here in the parenthesis, this is just going to be a power rule. We're going to bring the 2 down front, so that's going to be 2, times the coefficient that was there, quantity pi plus 4, and then it's going to be now x to the first power. The next term derives to a minus 8, and the 4 derives away to nothing. Okay, there's our derivative. What do we do with derivatives in this point? Set them equal to 0 and solve. So I'm going to move this up here. And this is a nice part. We can set this equal to 0. Well, let's divide both sides by 1 over pi. 1 over pi divides out here. 0 divided by that is gone. Now, let's get rid of this minus 8. Let's move it over to the other side and add. So that's going to be 2. Quantity pi plus 4 times x is equal to 8. Now let's divide by 2. So the left side is just quantity pi plus 4 times x is equal to 4. And to get x alone, we just got to divide by the quantity. X is equal to 4 divided by quantity pi plus 4. Now, in the context of this applied problem, that doesn't mean much. Let's punch it in a calculator and get an approximate. X should be approximately 0.56. Now remember, we did look at the feasible domain. We said it should be a number between 0 and 1. Looks like we found it, 0.56. That's beautiful. So that might be the max area that we're looking for. But remember, we did figure the feasible domain. We could do the area function of the left extreme, 0. We could do the area of the right extreme, 1. Or we can find the area of the number we found, 0.56. So again, we'll go back to the primary equation in one variable. In class, we would just put these in the TI-89. If you find the area at when x is 0, it's 1.273 squared feet. If we put in the other endpoint, 1, we get exactly 1 square foot. And if we put in our sweet spot, 0.56, out comes 0.56 feet squared. So this is the one that if we did not do the feasible domain and check the endpoints, it would have come back and bit us in the butt. But actually, the critical number we found was the worst of all the choices. If we did that, did sum in the square, sum in the circle, we would only have 0.56 squared feet of area. If we did everything in the square, if we used all 4 feet of wire to make a square, it'd be 1 by 1 or 1 square foot. If we use every bit of wire to make a circle and no square, we have the most area possible. So that is all circle. If you're playing around with 4 feet of wire and you want to maximize your area, don't bother making a square and a circle, just make the circle. Okay, and now we got one more example. This was newly added to this AP edition of the book. This is a good industry-based one. You've got a product that you're selling, the new TI Infinity calculator, and the product has a model of this. P is equal to 56e to the exponent negative 0.0000012x, where P is the price per unit in dollars, X is the number of units. What price will yield maximum revenue? So we want to maximize our revenue. We'll use capital R for revenue. What determines our revenue? Well, that's units times the price. The units is X. The price is P. So I'll write it over here. Units multiplied by price. If we're selling our new calculators for $100 and we sell 10 of them, our revenue is $1,000. So that is our primary. That is what we, in this case, want to maximize. Primary. Our secondary, there's not much to choose from. All we have left is this. That is our secondary equation. And I'm going to run out of room. I'm going to write it down here. P equals 56 e to the negative point. Let me double check that there are 1, 2, 3, 4 zeros. Negative 0.000012x. What price will yield max revenue? Okay. So we're going to take this primary, and I'm going to keep the x there. Revenue equals x times. We're going to take out that letter P and replace it with the stuff I wrote there in red. 56e to the negative point. Oh, I hate this thing doing decimals. 0.00012x. And I'm going to start a new slide so I can rewrite that and have more room to derive. Revenue equal, ooh, and let me do this too. Notice here we've got this 56 and we're multiplying it by base E and also by X. So I'm going to pair the 56 and the X together. I'm just going to rewrite that as 56X times E to the negative 0.0000012x. So there's our revenue function in one variable. We're going to have to derive it and set our derivative equal to 0. And in this case, there's no getting around it. We are going to have to use the product rule. And this is why I put the 56 with the x. Because if you derive 56x with respect to x, it's just 56. And if we derive e to this power, don't forget, be careful with the chain rule here. But when we derive e to a power, it's part of our derivative is going to be e to that same power. 0.000012x. We are going to need to do chain rule. We need to derive the inner function. So if we derive this exponent, the x just derives off. So here at the front, we're going to need to multiply that by negative 0.000012. Okay, let's do the product rule now. So dr dx, the derivative of revenue, the change in revenue as we change the value of x. We're going to do this one, 56x times this stuff down here. So that's going to be 56x times negative 0.000012 e to the negative 0.000012x. And then the product rule continues. I'll come down here with my plus sign. The other diagonal is 56 times that base e. 56 times base e to the negative 0.000012x. So that is our derivative, and we're going to set it equal to 0. And we could just type that into our TI-89 calculators. And you're going to get x is approximately 83,333 units. So remember, we defined x here as the number of products we're making. Now, on a multiple choice, that would be a decoy answer, 83,333, because that's units. The original question is, what price will yield the maximum revenue? So we would go back to our price equation. That's this one here I'm underlining in blue, and we would plug in that x value. P equals 56e to the negative 0.000012 times what we just found, 83,333 units. We punch that into the calculator, and you get the optimum price is approximately $20.60. $20.60. So that price will yield the maximum revenue for the product that you're selling. And that wraps up the video. Next time I see you in class, we're going to do some odd problems, and I got some good worksheets that we can try in class together. Alrighty, I will see you then.